In this problem, they give us the Maclaurin series for e to the x. So this is one of the series that we should know, but they actually just write it out for us. And then they tell us there's a function f of x, which is this entire thing here. And then they also give us f of 1 equals 1. And the function has derivatives of all orders. All that means is that the first derivative exists, second derivative, etc. Okay, part A says write the first four non-zero terms and the general term for e to the x minus 1 squared. So remember, since we know what e to the x is, all we're doing is replacing the exponent, which is the x, with x minus 1 quantity squared. So I'm going to go through and just replace the x and e to the x with x minus 1 squared. So the first term stays 1. Replace that with x minus 1 squared. And do that for the next couple terms. Notice if I plug in x minus 1 squared in there, squared times another squared really gives me to a fourth. I'm going to just go ahead and write it like that. If you don't simplify it, it's fine. And the next one will be x minus 1 squared cubed, which really makes this a 6. Okay, there's my first four non-zero terms, and they also want the general term. So take the general term. I'm going to plug it in x minus 1 squared, and then it's all to the n still. So there's my general term. So there's part A. Done. Okay, part B says use the Taylor series found in part A to write the first four non-zero terms and the general term for the Taylor series for f. So f is all of this. Now, a couple things. This piece I already figured out in part A. So it says we need to take all of that and subtract 1. So if you do just that piece, all that happens is that this 1 disappears. So, oops, I forgot to subtract the 1. So this would just look like this. Okay. Now, then, what are we doing? We are dividing every single term through by x minus 1 squared. So if I do that, notice your first term becomes 1 again. Then this becomes x minus 1 squared over 2 plus x minus 1. Remember, you subtract exponents, okay? And I do need 4 terms, so if you came up with one more here, this would have been x minus 1 to the 8th over 24, because it's 4 factorial. So the next term would be x minus 1 to the 6th over 24. And then our general term is x minus 1 to the 2n over n plus 1 factorial here. If you look at the pattern, this is really 2 factorial, this is 3 factorial, this is 4 factorial. So notice here I had to start on the top at n equals 0. So if I do that, I have to have an n plus 1 factorial on the bottom. Okay? Okay, so that takes care of part B. Part C, use the ratio test to find the interval of convergence. Okay, so you're going to take your general term from part B, and we are going to do the ratio test. Now, if your general term in part B is slightly different, this would be the general term if you start at n equals 0, but if you start at n equals 1, this is going to look different, and that's fine. Okay? Your ratio test will look slightly different, but your final answer will be the same. Okay? So I'm going to plug in an n plus 1. So if I distribute that n plus 1, it's really 2n plus 2 here. N plus 2 factorial multiplied by the reciprocal. Let's clean this up. You'll be left with just an x minus 1 squared really on the top. And then n plus 1 factorial over n plus 2 factorial just leaves you with an n plus 2. And we are taking the limit as n goes to infinity. So n is only on the bottom. So if you divide by infinity, that limit ends up being 0. So this is your ratio test. Ratio test says it converges if the limit is less than 1. You always end up with 0 here, so 0 is always less than 1. So in this case, your interval of convergence is all real numbers, or you could tell me from negative infinity to infinity. Okay, lastly, part D. It says use the Taylor series for f. So we came up with the series for f in part B. So you're going to look at part B. About x equals 1. That just means that everything should have that x minus 1, which it does. To determine whether the graph has any points of inflection. Okay, so when you hear those words, points of inflection, you should be thinking about the second derivative, right? That's where the points of inflection come from. So what I'm going to do is I'm going to rewrite our answer from B up here. So part B, we came up with this. I'm just going to write the first couple. Okay, so let's try to come up with the second derivative. So the second derivative would look like this. Bring down this, the derivative 1 is 0. The second one, bring down the 2, reduce the power by 1. Plus dot, dot, dot. That's your first derivative. To get to the second derivative, you would do the same thing. That drops out, right? So the derivative of x minus 1 is just 1, and then I can use the power rule everywhere else. Okay, now I only wrote the first couple terms, but what's going to happen is all the other terms will have all even powers. Notice here you have to the second, to the fourth. The next term will be to the sixth, etc. So regardless of what number you plug in for x, the second derivative is always positive for all values of x. So if that's true, you can't have a point of inflection. Remember, points of inflection can only occur where the second derivative is 0. There's no place where this is 0. This is always positive, so no points of inflection.